While it is certainly nice to have a decided upon strategy for simplifying non-perfect roots, whether that's square roots, cube roots, or roots of a higher index. While it's nice to have that strategy, there are certain shortcuts that we can exploit as we work through these examples and hopefully see, regardless of the index, that there are certain skills that are transferable to the different levels and indices that we're going to see. So obviously, because we're doing this work by hand, the majority of the roots that we see are going to be second, third, fourth, and fifth roots. But we want to make sure we're identifying those skills that are transferable to higher order roots. We don't want to just leave it at, this is a thing that works just for square roots. This is a thing that works just for cube roots. We want to expand our understanding of the root. So to get started, let's start with a really simple example. This is an example that you probably have some familiarity with from previous classes. This is the square root of 120. And what it is, you've likely learned that the process for simplifying this expression is to identify the largest perfect square that goes into 120. And the largest perfect square that goes into 120, believe it or not, is 4. When we separate 120 based on that perfect square, we understand that we are rewriting it as a product of factors. Now, we're going to see in a later example that the best way to do that for higher order ones is to maybe write out all of the prime factorization. But in this case, we were looking just for the perfect square. We identified our perfect square as 4, and the properties of radicals allows us to split that radicand into 2 separate roots, the square root of 4 and the square root of 30, leaving us with 2 square root of 30 as the simplified form. That's a standard issue Algebra 1 skill that you probably have some familiarity with. So let's up this a little bit to a slightly more challenging situation. A question like this: the cube root of 128 x to the 7th and y to the 6th. Now, the recommended strategy says to write out 128 as its prime factorization and then look for those opportunities to create groups of 3 that can be factored out to the front of the radical. So that's what we'll do. And hopefully after this, we'll discover a shorter way to engage this process. The prime factorization of 128 is 2 to the 7th power. So in here, we're going to write out 7 2's. When we move to the variable part, and we're going to do this, we're going to jump right to the split, so it's a little bit easier to see. When we move to the variable part, we're also going to have 7 x's, thanks to the x to the 7th power. There's our 7 x's, and we're going to finish it with 6 y's, thanks to y to the 6th. Now, the recommended strategy says to start making groups of 3. Because we are looking for a third root, we're looking for what factors go into this radicand 3 times. So we're going to make groups of 3 right here. Here's 3 2's. And we're going to make a group of 3 right here. Here's some more 2's. We don't have enough 2's to make another group, so we jump over to the x's. Here's a group of 3, and here's a group of 3. And again, we don't have enough x's to make another group, and we can make the 2 groups of y. Every one of those factors, then, that was just grouped, a 2, an x, a y, and a y, all jump to the front of the radical, as they were all cubed as factors of that larger expression. So we've got 2 and 2, which is 4, x and x, which is x squared, y and y, which is y squared, but we need to keep the radical for those last 2 terms, or those last 2 factors, the 2 and the x, that were not part of any of those groupings. So this is our simplified form. Now, a couple things you want to notice. First, if you would have caught that 64 was a factor of 128, 64 has a cube root, that cube root is 4, that's the same 4 that we see right there. If you would have caught that 64 was a cube root, or excuse me, 64 was a factor of 128, and it was a cube root that we know, you can jump that out to the front and move it out to the front, leaving behind the 2. We would have got to the same place. That's the same logic that we saw in this example. I saw the perfect square of 4, so I knew to move that. If you catch a perfect cube that goes into that constant coefficient, then use it. In this case, it would be a cube. Other cases, it would be a fourth power or fifth power, depending on the root. The second thing I want to make note of is what happened to the variable part. So we're going to look at that separately. Here's the variable part, and that's simplified to x squared, y squared, cube root of x. This is where our understanding of rational exponents can help us. Remember, this expression is really just this. And if we recall our power to a power rules, we get x to the 7/3, y to the 6/3. Well, 6/3 is easy, that's just 2. That's this 2 right here. 7/3 is a little bit tougher. It actually helps to think of it as a mixed number, 2 and 1/3. There's the 2, and there's the 1. So if you remember the rational exponent form of a root, if you can remember that that third root actually means the 1/3 power, then we have the option to interpret that variable part of the expression a little bit differently. Let's look at this in action. I want no part of writing out 47 x's and 93 y's and delicately grouping them into groups of 5. That is not anything I want a part of. So in the event that you have a situation like this, you are welcome to consider it as a rational exponent of 1/5. X to the 47 over 5, y to the 93 over 5. X to the 47 over 5 is 9 2/5. Y to the 93 over 5 is 18 3/5. The whole number part tells us how many groupings of 5 there are. The numerator, fifth root. The numerator tells us how many x's and how many y's are left over. There are some that just teach, hey, take those 2 exponents that are in there, divide them by 5, and figure out the remainder. You're only allowed to do that because of our understanding of the rational exponent. Do not confuse that. That is not just we're just going to decide to do this cold rule. No, we understand that that happens because of that rational exponent. Looking at another example, let's try another one that's similar to that, in that this entire binomial is being raised to the 14th power. That doesn't change our work at all. We have x minus 2 to the 14th power, thinking of that fourth root as the 1/4 power. That leaves us with x minus 2 to the 14 over 4, which is x minus 2 to the 3 2/4. Now, you need to resist the temptation to simplify that fraction. We need to know what that denominator is, and you can't just go changing the root on us. Okay, so we want to make sure we're expressing them in the root that we were asked for and with the leftover number of factors that we were asked for. There is something to simplifying that a little bit, but based on the way that these expressions are written, we want to make sure we maintain that root. So we're going to maintain this root of the fourth root, and that's x minus 2 to the 2nd power. Our principal concern in this particular lesson is to make sure that we're simplifying these correctly. Obviously, we have our extra concerns that we have established in other parts of the lesson with the absolute value and those different changes and all of that. We're more concerned with the actual skill of the simplifying than are we putting an absolute value in every single place that we need one. Let's finish with an example that let's sort of sum up all of these skills that we've established in these videos, things to look for. Now, could I write out the prime factorization of 54? Sure. Or I could use a little bit of careful thinking and say to myself, is there a perfect cube that's lower than 54 that I could recognize as going into it? And sure there is. That perfect cube is 27. So I split the 54 as 27 in two. Then I give my extra consideration to the cube root of a to the eighth, and I give the cube root of b. Based on the way that this is simplifying, I know that this b and that 2 are both going to show up in the final simplified radical as not having any factor to simplify, or not having anything to simplify with. I know the 2 and the b are going to be here. I take the cube root of the 27, which is 3, so I know that's going to be out here. I look what's happening right here. This is a to the 8/3, which is a to the 2 2/3. So that means I'm going to have 2 a's out here and 2 leftover a's in there. And this is my simplified form. So summarizing everything that we saw here, we're looking for those perfect squares, perfect cubes, perfect fourth powers that we could potentially simplify in here without having to write out all of the factors. And then we're using our understanding of the rational exponent to justify not having to write out all the a's and b's. I know I can jump right to those simplifications.